Good morning, all. This is Amrita from Locuz. A warm welcome to everyone, and thank you for taking the time out of your schedules to join us for this Locuz webinar on AI Tech Day. It's a half-day virtual event introducing you to the world of CUDA and its intricacies. With two specific technology sessions across the day, we get an opportunity to listen to NVIDIA experts as they share their learnings on two specific technology sessions. Session one would be about Introduction to CUDA-X and Computer Vision, Conversational AI, NLP. And the session two will be about accelerating applications with Open ACC, CUDA. So with that, let me present the agenda to you. We'll start the session at 10:15, and there'll be a Q&A session from 11:05, and we'll proceed with a small break from 11:15 to 11:30. We'll again resume at 11:30 for session 2, which is accelerating applications with Open ACC or CUDA. With that, I hope everyone is keeping safe and positive during these challenging times. Without much ado, let me just go over some of the webinar hygiene protocols. Let's keep ourselves on mute all the times for better audio clarity. You may please ping any questions you have on the chat box and we will take them up. To avoid the flow of the presenter, we will stick to taking all questions at the end of the presentation. With that, let me introduce Namrata. Namrata is an experienced sales professional and leader driving strategic initiatives for her region. She has been associated with Locuz for over 11 years and has played a key role in our growth strategy. With that, over to you, Namrata.
Thank you, Amrita. Let me just put up my slide. Welcome everyone to the session. Is my screen visible?
Yes, Namrata. Yes, it is.
Thank you so much. Good morning again, everybody, and a very warm welcome to all of you. Thank you so much for making time to attend this session. Artificial intelligence. It has gained a lot of prominence that one would have ever imagined, right? It is practically influencing every aspect of our lives so deeply and is so deeply intertwined in everything that we do. I would say so much so that it's easier to point out parts of our lives and our society that AI hasn't touched as yet. This clearly shows its importance in our daily lives, in business, research, and any other field that one can really think of. I would be taking you through a small presentation providing a corporate snapshots, the problems that we solve and the value that we add to our customers before handing over the baton to the NVIDIA team. This slide provides a snapshot of what we do, and very frankly, I can spend about half an hour on this slide, but due to paucity of time, I will give you a brief snippet of the overview. 20 years of experience has presented us with several opportunities to build and maintain complex networks, large systems, complex security projects, build large HPC environments, big data, and cloud. As an organization, we play a very key role in the digital transformation journey of our customers and have built the expertise in order to design large-scale, modern, and hybrid multi-cloud environments for them. We have been a pioneer in India building and maintaining large HPC setups right from conception to managing and maintaining it for our customers. We have gained a very deep understanding of their application and its environment and have acquired technology faster by partnering with technology innovators like NVIDIA, AWS, and the likes. And we help set up AI labs for our clients. We in fact help insert human-like intelligence into these machines in order to automate repeatable tasks, in order to detect and deter security threats and frauds, in order to predict user actions and suggest recommendations and the likes. Um, we deeply engage with our customers and help them establish effective AI strategies into their applications with the help of fast computing environments, which are specifically AI-specific infrastructure, um, AI-specific frameworks like TensorFlow, CNTK, AI-specific platforms like NVIDIA DGX, NGC, Amazon SageMaker, and also cloud-specific AI services like Amazon Recognition, Amazon Poly, and many more in order to quickly build, train, and deploy these learning models at scale. It could be on premises or on cloud. So talking about the problems that we solve, we engage deeply with our customers, as I mentioned, in terms of their AI journey. And I will be taking you through a couple of customer references and case studies and present the same thing to you. The first one I would like to start with is one of the Indian multinational conglomerates. They work on a lot of smart city projects. And as we are aware, one of the classic use cases is smart traffic management. So we have worked very closely with this customer wherein they are collecting footage from various video surveillance cameras. These are collected and analyzed on a DL platform through the ISVs in order to better enable traffic management. It could be in terms of diverting the traffic correctly, in terms of sending alerts to commuters, in terms of managing the timing of the signals, etc. So we tie up with a lot of these large SIs, including this Indian multinational conglomerate, in order to set up the AI infrastructure, which is the DGX1 at each of these smart cities. Next case study that I would like to run you through is of one of our customers who provides very meaningful data to their clients through NLP and have partnered with us for cloud formation. Now, one of the major challenges that they had is in terms of increased costs and the longer duration to in fact provision the resources to their customers, as they had individual physical infrastructure maintained for each one of them. Their entire goal was to ensure that they are able to provide these services on an immediate basis. And we were able to help them do that by setting up the infrastructure on AWS using SageMaker with underlying GPUs, MongoDB, etc. Now, through this cloud formation, they were able to instantly provision the requisite infrastructure along with the application packages in order to enable AI-based data analytics on cloud. So this became auto-scalable, it was automated, it was on-demand machine learning that they were able to provide. The next case that I would like to discuss is that of a non-profit organization that falls under the ambit of Government of India. They basically work on providing insights to farmers. They have partnered with us for the entire stack of NVIDIA GPU Cloud, which includes the DGX1 infrastructure and its associated software bundles, which helps them carry out image processing. There is some, yeah, thank you so much. This platform basically helps them carry out image processing, data crunching, and analyzing patterns in order to arrive at suitable incomes. So they have been running these applications and frameworks in order to be able to predict the best time to sow, the soil quality, rain, crop management, insurance, etc. The last case study that I would like to run you through is on one of the common problems that we are facing in today's world, which is deepfake creation. Now, deepfake creation poses the threats that we have mentioned here, which is celebrity defamation, scams, frauds, harassment, blackmail, manipulated posting on social media in order to influence various groups. And deepfake detection helps avoid all of this. The AIDL team of one of the institutes in Mumbai has conducted a research building convolutional neural networks for image processing and face forensics using the NVIDIA DGX platform, which has been deployed by Locuz. Now, we have spoken about the various cases where we have engaged with our customers through their AI journey, but our expertise goes way beyond what has been discussed this far. We in fact carry the expertise in terms of providing consulting and advisory services to our customers. We understand their vision, we help them choose the best suitable and cost-effective platforms. We help them in terms of sizing the right solutions, designing and architecting solutions, integrating the infrastructure. It could be the storage, the compute, the middleware, platforms, connecting all the nodes, data management, and much more. Over and above this, we also help them create an AI cluster in order to serve many users, meeting the requirements of compute, storage, and dynamic applications, which includes but is not necessarily limited to the head node, common storage, the multiple DGX systems that are connected over 100 Gbps of IB interface and managed through Kubernetes, CUDA, Docker, and the likes. We offer managed services that go beyond just monitoring and managing the infrastructure. We provide skill sets in terms of data engineers and data scientists. We also understand that machine learning and deep learning requires a lot of data and they need to be stored somewhere. We help our customers creating data lakes. We are partnered with the likes of AWS, Azure, Cloudera, NetApp, in order to offer data lake solutions or create customized solutions for our customers, and also offer IaaS and PaaS services. Last but not the least, I would like to run you through the innovations by Locuz. We have a group of engineers who have developed and engineered certain products that fall under the data center and high performance computing platform. I'd like to discuss two products of ours here, which is Clouter and Ganana. Clouter is basically an integrated software solution and hybrid IT orchestration tool that helps you manage, optimize, and economize workloads both on premises and on cloud just by a few clicks. Ganana being another product which comes in two flavors, which is our HPC app portal and the HPC cluster manager. The app portal helps the users to run the HPC applications without programming and the admin to manage the cluster, while the cluster manager helps the administrator to build Linux-based HPC clusters and manage it on the any x64 platforms. We as an organization have been constantly working on innovating and bringing more value to a lot more businesses by means of innovation. Hereby I end my presentation. Thank you so much. And I'd like to hand it over to May.
Is my voice audible?
Yes, Meg, we can hear
Okay.
you.
Just give me 1 second. I'm gonna share my screen.
Yes. In the
Let me.
meanwhile, let me introduce Meg to you. Mr. Meg Makwana works as a data scientist in the solutions architecture and engineering team at NVIDIA Graphics. He's skilled at applying accelerated computing to optimize data science workflows and deploying large-scale supercomputing clusters with MLOps platform. His research interests lie at the intersection of accelerated computing, self-supervised learning, and generative modeling for computer vision and natural language processing. With that, over to you, Meg.
Um, Hope my slides and my voice is viewable and audible.
Yes, very
Okay.
much.
Okay.
Thank you.
Hello everyone. Good morning. Thank you for taking out your time and joining us for the End Tech Day. And today, what I'm really going to do is I'm trying to give you a full perspective with respect to how we have not just built really uh, fast supercomputing infrastructure, but how the software platform that is built on top of these systems basically enable you to start taking all of these software components and start building your AI ML labs for the students. And then again, this entire platform is going to try to ease the work of the system admins as well as the researcher or the scientist or the students who are working on say any machine learning or deep learning problem. So I'll go through all of those specific software components related to computer vision and natural language processing, show you a couple of demos as to how using this software can students start building their projects as well as research papers using these platforms. So, as we all know, over the last 10 to 15 years, we have seen that the number of devices that people have started to use on a day-to-day basis have started to increase by a very large margin. Right about 1995, people hardly had, their own desktops and laptops. But today, this has become this is available with each and every student, parent, grandparent, everybody are using the PC, the laptop, as well as mobiles. And if you actually see the amount of data that is getting generated from these devices in form of unstructured data, like images, large corpus of unstructured text, videos, or audio, so on and so forth, is resulting in these large data source, and companies now need to basically take this data that has been generated by this large by such large amount of people. They need to apply some kind of analytics on top of this to provide an intelligent and seamless experience for their users. And that's why today in 2021, machine learning, deep learning, data science, and IoT have become the most important part of the curriculum and for the next generation of students to learn these technologies. And the major key factors behind the boom of data science or machine learning or deep learning in general is these three paradigms. The first is obviously the availability of massive structured and unstructured data sets. The second is the advancement in these machine learning algorithms. Now here, the term machine learning, I am using this term to include even deep learning, because deep learning again is a subset of machine learning. So the advancements that are happening in the deep learning space, specifically for extracting insights from this unstructured data, is advancing by a really large margin. And today, we can see all kind of different use cases, right from not just understanding what is there inside the image, but detecting where that object or the object which is of interest is present inside the image, as well as we are now also able to perform different kind of image similarity searches, as well as we now have really powerful algorithms to even describe or transcribe what is actually even happening inside the video feed itself. So these are just few examples with respect to computer vision, but there's a lot of different innovations also happening in the natural language processing space, in form of translation, in form of classifying what is the intent of a particular sentence. Is it a positive intent or is it a negative intent? Or rather, people also like to call it as sentiment analysis. Now, all of these innovations are leading to really large scale models. And because of these large scale computational models, there is a need of having these accelerators that makes sure that your training time and the inferencing time is as maximum for train is as least as possible for training and inferencing. So you need these accelerators to make your workflow run in a smaller period of time so that you can now enable the students to start experimenting with state of the art models and make sure that they are able to do these experiments within a short period of time. Now, if you actually see the applicability of these deep learning models for unstructured data, it has now gone from not just simply doing classification and detection, but it is now being used to solve these really complex problems, right from building video analytics application for smart cities, where we are now taking these large feeds of data and we are trying to process on each feed of data. We have multiple of such deep neural networks, which are trying to, do all kinds of different analytics on top of it. Now, obviously today, maybe in India this is not something that we see on a day-to-day basis, but at least in the US and other countries, we are seeing the adoption of self-driving cars, where companies like Tesla and others have started to do complete video analytics for managing the entire autonomous fleet of vehicles just using computer vision. And that's where you need to have the right computing uh, infrastructure, not just on the data center but also on the edge, so that you can process this large amount of video feeds that are coming in from these self-driving cars, so that the car can now take intelligent decisions based on these multiple neural networks that are working in tandem. Now, I believe that the most critical and the most impactful work that is happening using the applications of deep learning is in the space of healthcare, because today we have understood that healthcare infrastructure in India is not that well up to date, right? And that means the detection and finding out of these anomalous patterns inside these medical data formats that are coming in either in form of CT scans, X-rays, and others. We should be able to now apply some kind of classification, detection, and segmentation models on top of these different modalities of medical image formats to extract some insights out of it. And this is again going to reduce the overall time for you know uh, doing things like detection, prognosis, and also giving certain recommendations, so that the doctor as well as the patient can now start taking faster action. And again, still in India, you know use of these models have not become very ubiquitous, but soon in the next couple of years this is going to become the next big thing in the healthcare infrastructure. And obviously, the fourth one is related to smart industries. That means how can these industry processes that happens across the entire automotive and other industry verticals, how do we enable these machines with some kind of computer vision system that can aid them to solve a lot of complex problems. And few of the good example is anomaly detection, maybe on a conveyor belt, right? So say for example a company has a use case where they want to they are passing their products, and using a vision system they want to find out where those cracks are basically present. And again, this is just one example, but uh, you know having these edge devices that can perform these computer vision based tasks like classification, detection, and segmentation are now also becoming very crucial for the industrial 4.0 transformation as well. Now, generally, before I start and do a much more deeper dive inside the software itself, just having a quick view of how software was being written previously, versus what trend are we seeing in the future, and how does an machine learning or a deep learning program helps us to solve some of the problems which were not solvable in the traditional program. Now, if you actually see, the way we typically write program is, we write these different functions. And again, these functions are going to have some kind of a logic behind writing that function. That means the engineer has used his computer science knowledge and is trying to now solve, some kind of a problem using these different conditional statements. So in this kind of a programming environment, what we really do is the engineer or the software developer writes the rules of the program, and now you can take the inputs, and based on the rules that have been written inside the program itself, you're going to get some kind of an output. Now, this generally works very well on a lot of the use cases. But if we actually look at use cases like image recognition, detection, segmentation, where we ourselves don't really know what are the rules through which a computer, which basically sees these images as large matrices, can find out if there is maybe a cat or maybe a dog present inside an image, and if they are present, where exactly are they present, and to give the exact boundary of where they are present. And writing these rules have now become automated using machine learning. Now, what has really happened is, instead of writing these rules manually, we are now trying to take these mathematical models, which we call it as deep neural networks, which are really good function approximators. And when we say function approximators, it what I really mean is that they are able to capture the underlying pattern without handcrafting those feature sets on our own. And due to which, what is happening is, now instead of just passing the input, now you can give this ML program the input as well as the output. And then the ML program is obviously going to give some predictions. And then you compare those predictions with the real output using a feedback signal, typically called as a loss function. And using this loss, we try to find the gradients across all the different layers that are present in this ML program. And then we start the optimization loop. That is to make sure that the model learns after we keep passing more and more data to it. And this is roughly how the training phase really happens. And once the training phase is complete, you want to now take this trained ML program, and now you want to use it as the traditional program, which was, you just pass in the input and you're going to get some desired predictions. Now, generally, people also tend to ask this next question that, hey, what exactly are these deep learning black boxes actually doing? And, generally, if we see how taking a computer vision example of, say, classification and detection, previously people still were able to solve this problem using image processing techniques, where they use these hard coded image processing kernels, which will help you to probably find the vertical edges in an image, or probably horizontal edges in an image, right? So we used to use these handcrafted image processing kernels, and then we used to take these different features or convoluted output images and use those as our features to either do classification or to do detection. But now, using these deep learning black boxes, what we are doing is, we are trying to automate the process of feature extraction as well as the classification and detection in one single step. So all these image processing kernels that were previously handwritten, now inside a convolution neural net, are getting learned by the model. That means the user does not have to handcraft these image processing kernels anymore. These will be learned on its own, when you're trying to train these models. And today we are seeing a huge explosion of different model architectures that are coming in the literature. So convolution neural nets are very old, and they are really very successful in the space of computer vision. And again, we see all kinds of different innovations, right from newer CNN, modules. Like you have simple convolution, there are attention based convolutions and so on and so forth. So there are new variants that are coming out in the convolution neural network architecture, and there's a lot of different innovations happening in this space. We also have these different recurrent neural networks, which was used extensively a couple of years back for solving NLP based problem statements, especially when you have sequences of data which are interlinked with each other. And some of the use case could be again sentiment analysis, text summarization, translation, so on and so forth. But around 2018, we saw these new families of architecture called the transformer architecture, which I'll again talk about in a little more detail in the upcoming slides, that enabled that enabled the researchers to now solve those same NLP problems, but in a different way, and it also provides much superior performance compared to your recurrent neural networks. And that's why today you'll see that the transformer architecture are the de facto architecture choice for most of the NLP use cases that we see today. And again, if you're even looking at the latest literature in the past 3 months, we are now also seeing computer vision models being built on top of these transformer architecture. Then obviously you have the other variants like GANs, wherein instead of a single neural network, you have two neural networks, maybe a generator and a discriminator, which are basically fighting for an min-max optimization objective. And then you have these different reinforcement learning methods as well, using deep neural networks. And then you have these other newer species of architectures like capsule net, mixture of experts, and wide and deep network. Now, the core thing that that I want to present here is that all of these architectures at a very fundamental compute angle, if you actually see, are built out of these different mathematical operations. And if you see, the most prominent ones are going to be the matrix multiplications. And again, this can be in form of matrix multiplies, or it can be form of convolutions, or it can also be in form of these attention modules. If you actually also look at the attention modules, those are also built using these different fully connected layers only. So most of the compute intensive part is these matrix multiplies, and this is what the accelerators are really good at accelerating in training these neural networks. Now, also apart from this, you also have other operations for reductions, specifically your batch norm and other layers. And then you have these different loss functions like cross entropy, L1 loss, or the mean square loss, so on and so forth. And again, then you have the activation functions like ReLU, sigmoid, tanh, and so on and so forth. Now, what we have really so again, coming from the previous perspective that these are the kind of architectures that we are seeing, which are really very compute hungry, and what were the fundamental compute operations that had to be optimized. Now, again, solving and accelerating the training of these neural networks and optimizing the inferencing is one set of problem. And if you actually look at our software stack, especially above the CUDA-X layer, you'll notice we have these different CUDA-X libraries that help you to solve a specific subset of problem that I just previously mentioned. So for doing something like pre-processing, which we typically do on a CPU, when you scale your problem to really a large number of GPUs, you want to now also take the pre-processing step from the CPU and offload it on top of the GPU using the DALI library. Apart from that, you also have these CUDA-X libraries for accelerating the training of these deep neural networks. So like I said previously, you will have a lot of different variants of convolution operations. You will have different matrix multiply operations. We use these libraries called cuDNN and cuBLAS to accelerate those operations on the GPU level. And again, because these models are so compute hungry, we need to have a good communications library that can accelerate the multi GPU and multi node training on such large scale systems. And obviously at the end, I think one of the most not so taught point is the deployment part. Now, training is one part of the entire life cycle, but understanding how to deploy them is another ball game altogether, right? And again, this is what I believe that the students also need to be up to date with is, I know how to train a deep neural network, but then how do I really deploy it in the real world scenario? Because if you don't deploy it, it is not going to bring the value to the company where you're actually trying to work. So inferencing and deployment becomes extremely important. And that's why we have these specialized libraries like TensorRT and the Triton Inference Server that provides the basic building block for optimizing the inferencing performance. Now, on top of all of these, you have these deep learning frameworks that everybody must be using today, like either PyTorch or TensorFlow. Now, what we have done is we have understood that there needs to be a lot of industry specific software tools that are required for solving problem statements in those specific industries. So we have these industry specific application stacks right from healthcare called CLARA. For smart cities, we have Metropolis. For autonomous vehicle, we have Drive. For manufacturing, we have Isaac. For telecom, we have Ariel, and for conversational AI, we have Jarvis. And you know, because we need to teach students specifically domain specific SDKs, so that if a student is say interested in computer vision, but the domain that he wants to work in is probably not smart and safe cities or video analytics, but rather medical imaging, because the sort of problems that you see in medical imaging might be a lot more different than what you might see in a smart city or a video analytics use case. So choosing these industry specific and teaching these industry specific deep learning application frameworks are now becoming extremely important. And to make sure that people are easily able to use these libraries without having to install them from scratch, we have built an entire software hub called NGC. Now NGC is our software hub where we have provided all the software stack available to the end user, which they can now start using a containerized platform, which I'll talk about in a minute. So typically, in any organization, there are going to be two set of major stakeholders. One is going to be the system administrators who are managing those systems, inside your data centers. And the second sort of people are going to be the data scientists or researchers or students who would be using these systems for teaching or training and deploying these models. So we are going to look at each of these personas and we are going to see what software layer is extremely important for that particular persona. So let's start with the system administration. Now, typically, whenever we talk to a lot of different customers, especially in the HER space, we understand one thing is, managing the entire software suite is a very tedious task for them. That means, they are usually, they have to manually install it. They need to manually keep updating it as the new versions of the software come in. And this requires an update right from the driver level to the CUDA level to the application level. So it's a three-step process where just updating one layer is not going to solve the problem. And typically people have a lot of problem in managing the software because say tomorrow there is a new accelerated software that have come in, how to basically run it, compile it, and what are the best practices. Usually these things and being updated on this is a little bit of a hard task for the system administrators. Now to solve this particular problem, what we have done is we have built something called as the NGC app store, and this helps the administrators to just go on this particular app store and go and pull the required containers for the application that they want to use. And again, we have about 550 different applications available on this app store that they can go ahead and start using for their lab setup. Especially for deep learning, we generally see TensorFlow and PyTorch as the most widely taught ones, but you also have these industry SDKs like Jarvis, Metropolis, and CLARA, Isaac, and others that I talked about previously. And again, we also have a lot of these pre-trained models and training materials that is available for the users to start using and to start teaching in their lab curriculums. So you don't have to worry about keeping your lab ready in terms of the practicals, because all the most of the training and practical and Jupyter notebooks will be available to you via this platform. And again, I'll show a couple of examples of what a computer vision industry SDK looks like. How what kind of applications can you make out of it, and teach your students, and what kind of pre-trained models and containers are available for you to use on top of these platforms. Now, coming to why do you want to use containers? Now, typically, before I do a deeper dive, I generally like to talk about, why should today containers and mm, why should containers be taught to the students in any colleges? And the reason is simple, is because we are moving towards a cloud native infrastructure, wherein we are seeing that if we want to move an application from a system A, and say tomorrow we have a we need to show a demo on, say, system D, right? How do I safely take that package application from place A, from system A to system D, which is probably not there in the same city as where the system A was sitting. So say I have to go from Delhi to Pune for a presentation where I need to show a POC to probably some of the government agency for solving a particular problem. Now, I cannot, install all of those stack on the system which is present in Pune one by one, right? Now, what you can do is, using containers, you can now ship the entire software with the pre-trained model and the code from location A, that is from system A to system B, without having to install all of these dependencies on the system B that is there. And again, it will enable you to transfer all these different applications, right, from conversational AI, healthcare, smart city, to autonomous vehicle, to robotics, from any of the system A to system B. Now, the only requirement is that you need to have Dockers and the underlying GPUs available on both of the system. That is the only requirement that you actually have. Otherwise, moving these across systems is a completely a seamless experience. Now, one more point is that typically these containers, with every update of the toolkits, you also need to update the cuDNN, cuBLAS, Nickel, and the DALI layers as well, to improve the overall performance. And we update the software stack on a monthly basis, so you as a user don't have to worry about the latest version coming out on NGC or not. We update it on a monthly basis, and you can simply just run one command to pull the latest container with all the latest packages which are updated for the best performance. Now, that was with respect to the system administrators. Now let me talk about, how can these platforms be used for practicals and for students building their projects on top of these platforms. So let's start with computer vision. So in computer vision, we are seeing today that there's a really big industry, about $2 trillion worth of industry that is coming in, and a lot of video analytics use case maybe 5 years down the line were not being used extensively, but today every city, right from Delhi to Mumbai and others, everybody are moving towards a safe city infrastructure where we have these cameras, and where we are trying to do all these different kind of analytics either on the edge or on the data center. And again, this means that we need to run these computer vision based CNN models across these different places, and again, either on edge or on the data center. Now let's look at a couple of demos, because this will actually give us a good idea of what
is possible using the software stack that I'm trying to talk about. And obviously, you can take the same idea and apply it for other use cases as well. So this is a very simple, attendance monitoring use case. So let me quickly, run this demo. Just a second. So as you can see here, it's a simple entry exit attendance system where we are trying to track the people in a frame, find out how many people are present and how many people are entering and exiting from this particular area. Now, again, this is from our internal office where we are trying to, build this system. But again, you can take the same idea and apply it for a lot of different use cases as well. Now, another use case, again, which could be very prominent, especially during COVID, is the social distancing app. So if you actually see here, it's completely running on the video feeds. There are multiple deep neural networks that are involved. And, we have tried to, build these circle areas around the person that is walking, and we are trying to find out, is there an intersection between these circles, and if there is, we need to send an alert saying that the social distancing norms are not being followed. So these are just some of the demos that I just wanted to show, because this will just provide an idea of what kind of video analytics use cases are possible using these platforms. And again, this is exactly what we want the students to start building for their projects, so that when they go to the industry, they find these tools and SDKs relevant enough to deploy them in the real world scenario when they go to these companies. Now, what exactly happened in the backend is a multi-step process. And if you actually see, we can think of it as, training a model from either of these frameworks like TensorFlow and PyTorch. Again, where we want to accelerate and reduce the overall training time, so we can do multiple experiments. So we have these libraries called DALI and applying mixed precision, which is a way of doing the neural network computation, not just in FP32, but a mix of FP32 and FP16. And after doing multiple experiments, obviously you are going to come with a model that is highly accurate. So you take that model and then you apply some kind of inferencing optimization so that it runs in real time to give you almost real time performance. And that's where the TensorRT compiler along with the DeepStream SDK comes into the picture, where you take the entire neural network graph or the deep neural network graph and then optimize it on different levels, right from fusing the operations to reducing the overall precision from FP32 to FP16 to even integer 8 for doing low precision inferencing as well. Now, what do we provide is we provide you with really high performant pre-trained computer vision models that you might not find on just PyTorch and TensorFlow Hub. So we have these pre-trained models that are not available in general on any open source platform, which are highly accurate, and that will help you to optimize them on TensorRT and deploy them on DeepStream. So again, these are just a couple of them. There are more production ready models also that we provide, which can be used by the student in cases where they don't have really high amount of labeled data, because again, labeling is an extremely tedious process, and people don't tend to have this large amount of labeled data. So we are enabling the users with these highly performant pre-trained models so that they can start building their applications using our models. And again, we also provide a complete toolkit for people to start training their models for classification, detection, and segmentation, ranging from these different architectures that you see on the top, which are majorly for detection and segmentation. And on the left side, what you see are the feature extraction backbones. So typically in any computer vision system, you will have a backbone, which we call it as a pre-trained backbone, and then you'll have these different layers on top of these backbones for either doing detection or doing segmentation. Now again, we provide these wide range of model architectures and backbones so that students can start using the state of the art and start building use cases if they have enough label data as well. So, I talked about model training. I talked about the toolkits that are available. Now, let me also talk about that, just training the model is not the end of the story, right? Like I previously also said, you need to have an industry SDK that helps you to take these different multiple models, helps you to take multiple streams and perform all these different operations for building one end-to-end video analytics use case, right? From capturing those feeds from cameras or other sources to decoding those streams to applying the pre-image pre-processing steps like scaling, dewarping, and cropping, and then batching those frames in a four-dimensional batch and then sending it to the neural network for either detection, classification, or segmentation. Now, obviously, even post that you might want to do something like tracking and you want to display all these metrics on one large dashboard. So you can so this SDK that we provides you the enough tools and capabilities for optimizing your training with pre-trained models to also building an end-to-end use case for video analytics, right from the capturing of the live feed to decoding it to applying pre-processing to batching it to passing it to multiple deep neural networks and applying a tracker on top of it and visualizing those results on a large dashboard. So let me give a couple of examples of an end-to-end pipeline. So if I want to solve a problem like say number plate detection and recognition, I cannot just run an OCR and that is not going to solve my problem. In a live camera, you might see there are going to be multiple cars, right? So the first model that you want to run is something that just detects cars. And post that you want to now crop the part of the car that was detected using say a car detection model. Now this cropped image goes basically to the goes to the second detector, which is nothing but the number plate detector, which is the second model in the pipeline, which will try to find out where is the number plate on top of this cropped car image. Right now, after you have even gotten the cropped number plate, the third model that you need to apply is basically an OCR on top of this, which is nothing but a recognition model on top of this. And that's where you need for solving a problem of just automatic number plate recognition, you need these three different models running one after the another to solve this problem for a real video analytics use case that you'll actually see in the industry. And again, showing these examples and making students build these end-to-end pipelines is what is extremely important so that they know how to do all of these things even in the when they enter the industry. Similarly, I have another example for facial landmark and gaze detection that I've shown over here, but just in interest of time, I'm not going to go through all those details. uh, Post this, I'm going to talk a bit about conversational AI and talk about what are the general trends, what are the different transformer architectures that are available, and using our toolkits, what kind of problem statements can students start solving. So today, the biggest problem in natural language processing is that the models are getting really large. That means the total number of parameters in these models have gone from couple of thousands to millions to couple of hundred millions and now to even billions. And again, these are now becoming really big research problem statements that a lot of research institutes across the world are trying to solve. So how do we manage and accelerate training these really deep and large neural networks for natural language processing, as well as how do we also take these large scale models and deploy them in production? Again, these are two set of challenges when it comes to conversational AI. And if you actually look at India, we actually have a lot of big problems to solve in India itself. Now, the reason for this is because we talk a lot of different dialects across all the different states. So, today, the most widely used NLP, ASR, or TTS system that we see is always around English and other languages, and say maybe even to Hindi to some extent. But what about all the other regional specific dialects, that also needs to be taken into consideration. That means you need to have an ASR model for Marathi, Gujarati, Telugu, Konkani, Kannada, so on and so forth. Similarly, you need to have different natural language understanding or NLP models for translation, for sentiment analysis, for name entity recognition, for summarization, and so on and so forth for each of these domain or state-wise dialects as well. And again, this problem or the conversational AI problem, at least in India, is I think going to be the biggest thing that we can actually solve, with the help of students, by not just building highly accurate models, but by building these large scale corpora of text as well. So if you actually look at a conversational AI application, there are typically three steps that we see. The first is the ASR, and even in ASR, you will have these three different workloads, right from the feature extraction, wherein you take the raw WAV file, extract out some features, then you move it to an acoustic model, and then from the acoustic model, you pass it to something called the decoder. Now the decoder is going to convert these this wave files from speech to text. Now again, when the decoder is decoding each part or is converting it from speech to text, you also need to compare that, is the grammatically, is the sentence that I'm trying to create using the decoder, is this correct or not? And that's exactly where a language model comes into the picture, where a language model can help you for either doing the next word prediction, or it can help you to even correct the grammar of the sentence itself. So a language model along with the decoder helps to get robust conversion from the WAV file, that is from the speech to text. Now, once you have this data in the text format, you can now apply any natural language understanding model like translation, query search, visual search, autocorrect, search ranking on top of this. And again, it can be any transformer architecture that I previously talked about, like BERT, probably GPT architecture, or even the latest, architectures that are coming in, that are being used extensively, which I'll talk about in a bit. And post that, once you have applied some kind of smart analytics on top of the text corpus, like say just an example of say translation, where you translate it from English to say Hindi, now you can take that Hindi written text, that is the output of the NLU system, pass it to a text to speech model that will take that Hindi text and convert that into human like speaking wave back again, right? And that's why we call it as text to speech. Now to solve this problem, one of the biggest problem is having enough label data. And again, this is a problem that we see across all the different enterprise companies as well as government companies with whom we work, when they are trying to solve these problems that, hey, we don't have label data. But the good thing is we have this new learning paradigm called self-supervised learning. And what self-supervised learning basically means is now you don't need to have human annotators or labelers who can label the data for you. You can just use the input X, which is the raw corpus of input data, and now you can make these pseudo labels from the X or from the input data itself. So one of the best example is training a language model. Now, generally what happens in a language model is you want to do the next word prediction. Now, if you take a large unlabeled corpus of text, you can now simply, have the first four words as the input word, and the next set of four words as the next sequence of word. Now, the Y label that you have created here is created automatically just by by writing some, a code of changing the index by a certain scale. That is all, right? You did not have to label it manually, but just by using a computer program and shifting the index by few locations, you can now create these pseudo labels Y. And that's why, at least in the NLP space, we are seeing a huge adoption of language models, of training these large language models in an self-supervised learning methodology. And similarly, you can also do that for computer vision as well. If you don't have a lot of label data, you can simply apply different kind of training techniques like contrastive learning, where you might apply some kind of image distortion on top of the input image, then feed these two images, which is the one with the distortion and one which is the original, and pass it to a neural network to say if both of these two images are same or not. And by using this contrastive learning, we still learn some, hidden representation that can be learned by the neural network itself. And again, you don't need, labels for this. You can simply apply a CV2 or a open CV transform for distorting the image as well. So self-supervised learning is becoming extremely important. I also want to talk about the transformer architecture as well. So here what you see is in around 2017 and 18, this paper called Transformer came out. And again, what it tried to solve was these, natural language processing tasks, which were previously being solved using RNNs. Now, instead of an RNN, can I now use multi-head attention modules along with feed forward network to solve problems like translation and others. And to the surprise, what we found out in these papers was that these transformer models first could capture long range dependencies. So one of the problems that we saw that was there in solving these NLU problems was that it was not able to capture these long range dependencies in a sentence. That means how does one word which was say after 50th location be related to the first location in a particular context. So to find or to have these relations across the words in an entire sentence, you need to have something called as a self attention model that can pay attention to the entire sequence of word and try to find the relation between them. And if you see, this transformer architecture leverages a very fundamental or has incorporated a new fundamental operator called the multi-head attention model. And again, this became extremely famous because of the extent to which it could capture the long range dependencies. Second, it was more effective with respect to the computation, because now you can take the entire input sequence all at once rather than passing it one by one in case of an RNN or an LSTM architecture. And again, this provided state of the art results on really big NLP problems as well. Now, generally, we see that there are two models that people generally talk a lot about. That is the GPT and the BERT architecture. Now, and people also tend to confuse between the GPT and the BERT architecture. So I'm just quickly going to do a demystification on this. So if you look at the transformer architecture here on the left, it is built of two blocks. One is the encoder block and the second is the decoder block. Now, if you look at the GPT architecture, it is based on this decoder block only. It does not use these uses this encoder block. It's basically unidirectional. And when I say unidirectional, that means it cannot see the context far in the future, but it can only see the context on the left side to what has been given to the GPT model. But if you see, GPT is really good at doing text generation. And especially today, if you look at the GPT-3 videos on the internet, you'll be astonished to find out that it almost, gives human-like text that can be generated from this GPT architecture. And then you have the second architecture called the BERT architecture that uses the encoder part of the transformer, which uses something called as the multi-head attention. And these models are also really good at solving a lot of different NLP tasks like text classification, name entity recognition, and so on and so forth. And again, training these models, because they are so large, requires huge amount of compute power for building these for even training and fine tuning for any downstream task that you have that you want to solve. So let's talk about how are we trying to solve and how are we trying to make sure that the users can start using all of these models on top of our platform. So what we have done is we have provided a lot of state-of-the-art models for ASR. So we have provided highly accurate models for like Jasper, QuartzNet, and CitriNet, which is available to you to for students to start using. We currently only have support for English, but you can obviously start building these models with the students, with the student community, for start building it for your for the state specific dialect that you are interested in. So we would be really happy to see colleges coming up with ASR built on Jasper, QuartzNet, and CitriNet for say Marathi, or say for Gujarati, or say for even Kannada, or so on and so forth. Similarly, we have these TTS models specifically for English, and we would really love to see the research community coming up with TTS models specific to Hindi or even other state specific languages. And similarly, we also have a lot of NLP models like BERT, GPT, and Megatron for solving things like name entity recognition, text classification, question and answering, intent and slot, as well as punctuation. So all these English-based state-of-the-art models are available on our platform, and you can use these models on your domain-specific data set for solving your problems as well. And that's where we have this entire framework called Jarvis that helps you to take these highly accurate pre-trained models, retrain them on your data set, and deploy them as chatbots or voice bots, right? And again, this is now possible where students can start at least with building these pipelines only on English data. And obviously, as future research, you can also build it for domain specific language, sorry, for state specific languages as well. And that is exactly what we would be very happy to see, that the research community in the India brings out these state of the art models for these dialects as well. So all these resources for using these pre-trained models, Jupyter notebooks, all these can be incorporated in the labs that are there that you are teaching currently, either for computer vision or NLP. All of the Jupyter notebooks, all the documentation, all the blogs, we provide all of this so that you can get started on your journey and start incorporating these Jupyter notebooks without inventing everything from scratch. So you can use these notebooks for teaching the students, and for students to take these and then go back, collect their own data, and build their own use case as final year or research projects as well. So I would like to end by showing a quick demo of Jarvis and showing you what exactly is possible and what kind of use cases can you build using our platforms. So let me quickly just show a quick demo of Jarvis over here. And let me, okay, one second. I think I need to share the audio as well. I think that is what is missing. Just give me a second. Include computer sound and uh, yeah. Can everybody see this, water droplet, blue colored water droplet?
Yes.
Okay, awesome. So let me play the video and let me know if the audio is not audible. I'll increase the volume, but this will give a good idea about how you can start building your own conversational AI application using our platforms.
What do we think we're looking at for Wednesday in terms of layout?
这个设计的整体结构图是在没有包装或是模型前执行的。我们会需要一点时间改动。
Well, if you like, I can set you up with an optometrist to get an eye exam.
That'd be great.
Okay, no problem. We'll get you started with that. I see Dr. Lee's office is close to your home. She's really well rated in our network.
Is it snowing in Chicago right now?
In Chicago, it is currently not snowing.
I'm actually planning to visit there.
That sounds like a lot of fun. What else are you planning to do while you were there?
Find us a Mexican restaurant.
The nearest Mexican restaurant is Luna Mexican Kitchen, located at 1495 The Alameda, San Jose.
How's the weather in San Francisco?
It is currently 66 degrees and sunny in San Francisco.
My name is Misty. Nice to meet you.
What can you help me with?
I can help you with current and upcoming weather at any location, and can also provide interesting information on meteorology.
So that's how, and again, this is not all just, in form of just videos. You can actually deploy all these pipelines on top of our platforms, and, students can basically, take these models and train it for their specific use case and start building their projects on top of this. So I think I've anyways, overshooted about 5 minutes. So I would like to hand back the baton to the Locuz team. And if there are any questions, please let us know. We'll be happy to answer them.
Thank you so much for that, Meg. And what an amazing session. So we are open for questions, and we would really appreciate, we'll go ahead and take some time for questions now. Just a reminder, please be sure to type your questions in the chat box in your control panel. You may unmute yourself. If you have any questions, you can ask.
Hello, am I audible?
Yes, you are, ma'am.
Yeah. Can I know that is it open for the community or is it free accessible for any students or the researchers?
That's correct. Yes, it is open for the community. The only requirement is you have the GPU infrastructure in place for running these applications. That's all. That is the only requirement.
Okay, sir. Thank you.
Hello. Hello.
Yes,
can you hear my voice? Yeah.
Yes.
I'm a central government employee. I'm also. It's a very good demonstration you have given, and I'm a AI specialist working in collaboration with DRDO in Hyderabad. I'm from MSME, Ministry of MSME. Actually, I have a small question. Like you are pointing about towards the students. So most of the students, they are requesting, they are very much interested to take on Nano, Jetson Nano. So my question is, will these applications are supportable on Nano or higher end?
So a good question, sir. Basically on Jetson Nano, based on the form factor that it has, it can support computer vision models like classification and detection. But when it comes to deploying these NLP based models, because we know that these require large amount of compute, it won't be possible to deploy the NLP applications on Jetson Nano. For that, you might either have to go for the Jetson Xavier NX or the Jetson Xavier itself.
Okay, and is there any possibility, like if the user is having a high-end his own laptop and the specific operating system like Ubuntu?
Sorry, sir, I could not understand. Can you please repeat?
Like suppose instead of this Jetson, if the user can also use on the laptops or on his own PC.
Sir, again, it would depend if there is a GPU card available. Also, it would also depend based on the GPU memory and the SMs which are present, what kind of models can be run. So just as an example, if I have a in my laptop, if I have a 4 GB GPU card, but my BERT model might take say 6 to 8 GB of memory, at that moment I will not be able to run it. But yes, any model which is less than 4 GB, I should be able to run it over there. Yes.
Okay. Okay. Thank you so much.
Hello.
Yes.
Yeah. So I have a question regarding what is the oldest GPU card, NVIDIA GPU cards, GPU cards which is supported. Can you work with Tesla 2050C, or do you really have to have the newer versions of?
Sir, see, basically with our Volta architecture, the Tesla Volta architecture, we introduced these specialized hardware cores called tensor cores that enable the training and the inferencing of these deep neural networks. So any card before Volta might not, might not work because of the compute capability issues over there. So you would need at least a compute capability of 7.0 plus, that is after Volta and other next generation.
So okay. So what's the cheapest? See, these are the practical questions, because if you are targeting the students and the faculties of a colleges, you have to specify what is the cheapest GPU card they can work with.
Correct. So I think that is something the Locuz team would be very happy to help you with and work with you to understand your requirement. So I might not be the right person to talk about the commercials here, but I think the Locuz team.
I mean, what I am asking you is that, is there a particular versions or of a particular number of the card which is from which onwards it would support? That's the question which is there. I think it is there for the variety of audience. This is the most practical questions, because many of us are from from the academic and probably cost sensitive organizations.
Understood, sir. So, sir, you will need at least any architecture above Volta. That is what we recommend for running these applications.
Okay.
Meg, can I just elaborate a bit on that?
Yeah, sure, Isaac.
So basically, it is spread across as architecture. So for each segment, let's say for enterprise sector, that will be our Volta cards in enterprise sector. So V100 onwards. And you'll have it in similarly in the professional use space as our RTX cards, and in the consumer space as the RTX, again, consumer level cards like 2060 onwards. So generally any card which
the RTX 20.
No, don't quote me on it, but I would suggest at least 2060.
26. No. See, as you can understand, I am asking, this is a very, very practical question.
Exactly.
Of course, the enterprise would go for higher GPU RAM and this thing, so it does not affect that. But to begin with, for a college faculty to procure a A100 or V100 is going to be a tough.
Sure. But yeah, I thought I'll just clarify that, but Locuz team will take it forward if you have any.
Yeah, sure. Okay. Thank you.
Sir, may I have your name?
Yes, it's Meg.
No, Meg.
Oh, sorry.
No,
Yes,
you want my name?
Yes, sir.
Yeah, I am Akash. I am in touch with Locuz, so that's not.
Sure, sir. We'll get back to you on that, and we'll get in touch with you.
No, we are getting, probably we will be procuring a cluster. So that's not a question per se with me, but it is a very important question for the people who are from the academic college background. Okay, so even for us also, because suppose we want to put these low end, low cost driven thing for model development, and for actual number crunching, this might move to a server which will have probably A100 or V100 on them. So that is not a problem. But what we want is a low cost a model development which is there in a workstation. Okay, so that we do all the tinkering on that. Once we finalize it, we move it to a server which has V100 or A100 to do the work.
Okay, sir.
You understood now?
Yes, sir.
Yeah.
Sir, excuse me, Akash, sir.
Yeah.
Actually, I am a industry person. So better, I suggest instead of going for the GPU memory card, okay, the low cost, very low cost is the Jetson Nano. It is a very good device because even DRDO, when started working in the ML, okay, even we started first with very low cost, that is Jetson Nano. You can do almost all the applications on that, and then you can forward that total application to the server. The server
yeah,
belongs
so
to
that's
AWS.
that's the idea of it. See, this may not be very exactly relevant because we intend to buy A100 or B100 cluster, but this is pertinent for practically from my students. So I wouldn't put my server in jeopardy by putting
that's
in
the
for all the
reason.
test bed of the thing.
And that's in the student point of student fraternity, because the students may be doing a lot of wrong things, okay, a lot of
Right,
research.
that's precisely we want.
So for that, the robust design is the Jetson Nano. You do whatever you want, the Jetson Nano will not corrupt. And the only thing you have to spend is one-time investment, for example, for 10,000 to 11,000 rupees, for example, if one piece of Jetson Nano, for that at least only the SD micro card, which supports from 32 GB to 1 TB. You can simply change the cards for each and every application, and you can do whatever you want. The student can do it. It's a very robust one, and also it consumes very less power, and it is not so heated also, because we have tried everything on that.
Yeah, so this is another problem which we are facing with the workstations, that gradually initially they have a less heat issue, but with time I am seeing that the heating, so we are making our own jugaad to. This is for workstation, not for the server. Server will be obviously it will be enclosed in a cooled rack, right?
That's the
liquid
reason.
cooled
So
rack.
I suggest don't use the workstations. Better you shift towards the Jetson Nano, because it's a very good GPU. I suggest, because I have practical experience on that. Okay.
Thank you for your suggestions. Thank you.
Sir, thank you for that. I really appreciate it. And sir, may I request Alok sir to help us address, if possible? He is our HPC expert over a decade, sir. Alok sir, can you please help us out here?
Hello. Can you hear? Hello.
Yeah.
So I think till that time, can we just take one more question? So there's a question of the Dockers and containers are not workable and backward compatible. Could you please just elaborate? Because I mean, this might be due to very specific things that might be happening, but we have not seen this issue happening at any of the other customer places. So can you elaborate why are you facing this issue?
We have just set up a new center for artificial intelligence. I am working also for the government, where we will have to give results. We are not students. We don't have failure as an option. Okay. So anything which is working, we want to implement it immediately and get our results. And when we see it's available in the form of a Docker or a container, we get it in and we want to do a POC. When we get it in and try to do POC, the Docker itself does not install or workable. Majority of the times when we are working on a project, suddenly I come in the morning and try to switch on my Ubuntu machine, and the machine says there's no graphics card available or driver available, because everything has migrated. The old driver of whatever graphics card I have got, CUDA or NVIDIA, everything is not compatible, and Ubuntu drops it. There is no way that automatically it gets upgraded when the system upgrades. The way you explain, it seems it's a click of a button. That does not actually happen in real world scenario. It's very difficult.
No, I mean,
if I develop some
sorry
environment, it does not go
Yeah, I
hand in
think
hand.
this
If I want to move it to a production environment, and if I want to move it to an offline machine which are actually not connected onto the internet, onto a machine, again, movement of that entire environment is a questionable affair.
I'm not really sure. There might be something funny additionally happening. I'm sure this, because we have not seen this issue happening at any other place. I mean, we would be really happy to understand your issue in more detail. If you can just drop us a mail, and we'll be we will be happy to just understand, because see, from what I understand is the driver sits outside the container. So essentially the driver is going to sit on top of the Ubuntu OS, and the CUDA toolkit and the application sits inside the container image. So what might be happening, and again, we have seen some people going through this issue, is they might be additionally installing newer versions of drivers, or probably installing via Conda, even when they already have PyTorch and TensorFlow inside the container itself. So I believe that something might be going wrong, but we have not seen any other customer facing this issue. I mean, if you can just drop us a mail, I'll provide you with our mail IDs, and we'll provide you with a good methodology of how you need to go about installing Dockers, and probably some of the best practices that we follow.
Can
So,
this be can this be overcome by scheduling the not doing an automatic update, but scheduling upgrade? So that means that you don't do immediate triggered update as soon as it is updated, but
No,
have a schedule of
actually
update when you are aware of
actually the
compatibility.
problem is not. The problem is that Ubuntu moves on. The drivers we don't upgrade. We don't want even to migrate from 16.4 to 18.04 in Ubuntu, because I had a lot of questions whether my system administrator came and said it's a cybersecurity violation. You're you're still in 16.04. So I was not sure whether my entire system will work or not, because I have got around 12 environments managing around that many projects. And if I migrate, I was doubtful that and I will find an NVIDIA driver which will work on the system, because I do not get access to my system itself, because NVIDIA does not work, because we have to retire the original graphic driver which is there in Ubuntu to install
again,
NVIDIA graphics card.
I believe it might be some issue from the system administration side. I'm 100% sure on that something might be going wrong. I mean, can you just mention what machine are you using currently?
It is Dell Precision.
Okay, and which card is there inside this Dell Precision? Sorry?
P4000.
P4000. Okay, sir.
P4000.
Got it. Can you just drop us a mail, and we'll be happy to share some of our learning and try to help you find out with the admin where exactly this issue is happening. But trust me, we have not seen any other customer either in the HER or enterprise or other spaces facing the same issue. So I believe this might be an issue from the system administration side.
System administration is not. I have removed them because they only come for audit. I am the administrator of my machine. Full rights are with me. So that question is deleted, because that option does not exist. He just comes to audit. He only points a finger at the audit time.
So sir, we can just quickly have a maybe a team viewer or some session, and we can just help you find out the root cause of this. So just drop us a mail and we'll be happy to help you out.
Okay. Thank you.
Thank you, sir. Meg, we have one question from Dr. Abraham. Is there any platform with a GPU facility available for students to run their codes?
On cloud or I mean, are we talking about? Are we talking about
mentioned?
On cloud.
Oh, it's on-prem, right? Sorry, I could not hear you. I lost your voice. Can you come again?
It's on cloud.
I think in that case, you can just talk with Locuz team, and Locuz team might be the right people to guide you here.
Okay. I'm actually from a academic background, and am I audible?
Yes, ma'am, you are. Yes.
Okay. Okay. So we are working in a rural area where I'm actually working on a machine learning. So some of the students, if they want to, earlier I worked in an institute, so there were we can access the clusters, GPU processing machines, but here it is sometimes difficult. So that's why I just asked whether some facility available for the students to do some of their exercises.
Understood, ma'am. Ma'am, I think Locuz team can help you out on those parameters.
Okay. Yeah.
Yes, ma'am. We will get in touch with you on that.
Okay. Thank you.
You're welcome, ma'am. And we have another question from Sony. Says like a few problems where localization into a regional language would work well on currently built system like SOTA. Is there a kind of AI problem that you expect to be harder because it's in a different regional language than English or say Hindi?
Yeah, so we see this problem a lot, specifically in regional languages due to multiple factors. The first obvious problem is the availability of enough data in digital format for that particular language. Second is solving the sub dialects inside that. So even say Marathi, people speak different kinds of Marathi as well, right? So and the tonality and everything is different. So again, based on the problem that you're trying to solve, either it's a speech problem or an NLP problem, the data obviously is the biggest bottleneck in solving them. And the second issue can be based on if it is ASR and TTS. The issue could be with respect to different ways in which it's been spoken and having enough data for that. And for TTS, it might be the tonality in which it needs to be interpreted and be spoken out. So there are a couple of challenges that we expect with respect to these regional languages, which I believe is a pretty difficult problem to solve. And we are working with few organizations to solve this large problem statement.
Thank you, Meg, for answering that question. And for it looks like we have covered all of our questions today. So, Meg, is there anything else you wanted to cover before we wrap up for the first session?
Sorry, I have one small question.
Sure, sir. Please
This
go
is
ahead.
Shivakumar. So I have a small question regarding the application part, not the system part. The question is,
Sir, I lost you. Your voice is cracking. Is it just me or?
So we are not able to hear you. This. Sir, are you there? I think we lost him due to some technical issue. Okay, we have his question. Meg, we have another question here. Meg, can you hear me?
Yes, I am looking into the question. I'll need a minute to go through it.
Okay, sure.
So Amanji, what you'll have to do is you'll have to use something called the DCGM on top of this. Obviously, as you correctly mentioned, NVIDIA SMI only gives you stats with respect to GPUs. If you want it, if you want to capture more in detail stats of the system itself, you will have to deploy something called DCGM, and then basically connect the DCGM operator to probably tools like Prometheus and Grafana, where you can load that in probably a database and then make visualization charts on top of the Grafana dashboard. So I'll probably share some links that would be helpful that you can go through.
Sorry, my connection got lost. So the query I was making was, in the most of the convolutional neural network applications, I saw only the identification of the object. But what about, say, if I want to identify the orientation? So let us say, for example, I'm working on vortices and I want to identify whether the vortex is rotating clockwise or anti-clockwise. I mean, how about such applications using convolutional neural networks?
So there is a family called CapsuleNet that I have seen people use CapsuleNet specifically for capturing the orientation, as you mentioned. because again CNN has some problems with respect to understanding the orientation in a proper format. So I think CapsuleNet is something that you can explore.
Okay, thank you.
Thank you so much for that, Meg, and thank you, sir, for the question. And as we are running out of time, so we'll move on to the second session. And for that, let me introduce Mr. Isaac George. He specializes in providing robust solution for HPC requirements in his role as solution architect at NVIDIA. He is experienced in CUDA and related HPC technologies in NVIDIA's software platform. His work is focused on accelerating and optimizing large-scale applications in scientific domains like weather and CFD. With that, over to you, Isaac.
Yeah, hello, am I audible?
Yes, you are.
Yeah, let me just give me a second. Let me share my screen.
Sure.
Yeah, is my screen visible? Slides?
Yes.
Yeah. Okay. Almost good afternoon. So good morning, everyone. Still. So my name is Isaac George, and today I'll be talking a bit about OpenACC and CUDA. So just to give an introduction on why this is relevant in AI. So when you talk about AI, you generally have high level APIs as well as SDKs to make do with all your most of your applications, right? But in some cases, you do need to get down to the GPU level. You need to understand a bit about the GPU computing, as well as the different underlying technologies, as well as different hardware level features that allow you to accelerate your application. So today I'll be just going through in a very quick detail because this is a very huge topic to tackle in less than like 45 minutes or 1 hour. So I'll be just going through an overview of what makes the GPU tick, what accelerates your applications, and what is the basic CUDA fundamentals that allow you to do your GPU computing. And if you don't want to go to CUDA level, how can you still make do? What are the other technologies that are available that will help you accelerate your application? Right. So this is mainly covering the bottlenecks, and this is more of a performance-oriented presentation. So let me start with that. So when you talk about GPU, it has always been a full stack optimization problem. So as one of the previous questions was coming, you do have operating system upgrades that do happen every for LTS versions, you have every 5 years for Ubuntu. So whenever that upgrade happens, you do get some new features which come along with that. You also get new optimizations done in the library levels. So all these have to be propagated up the software stack. So when you have a OS upgrade that has any new features that comes, has to go up the chain. So basically it will have to go to the CUDA, then it has to go to the other libraries that depend on CUDA, and then it will be useful in the applications that depend on these libraries as well as CUDA. So that is how we were able to achieve these huge numbers, as in like 100x performance improvement over the time for applications which from the time when GPUs were introduced. So it's not just the improvements in GPU architecture, but also the different software that rely on it and optimizing that as well. So just a quick overview of the NVIDIA Universal Acceleration Platform. So at the base level, you have your GPUs, you have your consumer grade, your professional grade, as well as enterprise grade GPUs. Also, you have OEM systems as well as the cloud infrastructure available. On top of that, all NVIDIA GPUs allow GPU computing through CUDA. That will give you the best performance. It does allow other things to run on it as well, but CUDA is what gives you the best performance on NVIDIA GPUs. So running on top of CUDA, we have for different set of use cases, we have HPC based libraries, you have deep learning based libraries, and you have ML based libraries. On top of that, we do again have already coded applications and SDKs like PyTorch, TensorFlow, which do have a GPU backend to be able to accelerate them. And finally, on top of that, we have the customer use cases where you have the industrial applications, scientific applications, and IoT-based applications. So how does now, is anybody on speaker? Can you just mute it? How does GPU acceleration work at a very low level, right? So let's assume you have a C program or a C++ program or a Python program, right? So generally what you generally have is you have a very huge application, which are a short application, but in most cases, only about 5% of your lines of code will be actually compute intensive operations, okay? And in this 5% of your code, most of the code will be most likely parallelizable. So this, so for the lines of code which fits these parameters, that is, one is should be compute intensive, and second, it should be parallelizable. Those are what we try to move to GPU, and that the rest of the sequential code should remain on CPU, as GPU is just an accelerator, and that's how you accelerate your entire code flow. Now, as I just mentioned, both CPU and the GPU works together to give you the best performance, as CPU is optimized for serial tasks and GPU is for parallel tasks. And just a quick touch on the strengths of CPU as well as GPU. CPU generally has very large memory, so you can load most of your data there, and very high clock speed and latency is optimized. Some weaknesses are low performance per watt. As you increase the clock speed, you exponentially increase your power requirements, and it has a relatively low bandwidth, memory bandwidth. And for GPU, the strategy is entirely different. The architecture is entirely different. You have a fixed amount of memory, very high speed memory though, and you have high performance per watt. And at the same time, you do have less performance per core, but the overall throughput is very high, as all the tasks are done in parallel. So that I just covered a bit about what makes the GPU different from the CPU. Let me come to the GPU. So here is where I talk about the CUDA. So what is CUDA? CUDA is our general purpose GPU computing, which performs the best on NVIDIA GPUs, which gives you the best performance on NVIDIA GPUs. And this is done at the same time when you retain your OpenGL and graphics performance, right? So if CUDA is enabled and you lose your graphics performance, it won't appeal to most of the users. So what is again, CUDA is again based on industry standard C. Now it has migrated mostly to C++. And it allows for a handful of language extensions to allow heterogeneous programs. Now, what is the relevance of this in SDKs like Kubla, CUFT is basically all your code, all your backend code is written in CUDA-C, and all the Kublas, CUFT, your CUDA-NN, everything will provide you APIs or wrappers to able to call this backend CUDA-C code, right? Now, a few basics to understand the rest of the section, a few terminologies. One is host. So whenever I talk about host compute or host memory, I'm referring to CPU. So that is your starting point always. So your CPU and its memory, device refers to, in this particular instance, GPU and its memory. Let's start with something very simple. Everybody knows this is just your basic hello world program. In any language, you basically start with this, right? So this particular code here is in standard C, which runs on the host. So that's your CPU, right? So right now you don't have any GPU code here, and NVIDIA's CUDA compiler, that is NVCC, does not complain at all when there is no device code, because in basic CUDA, it is just basic C, right? Now let's see a code with device code. So here you will see two notable additions to it. That is the kernel call here and its corresponding definition, right? So let me just explain a bit on that. So what you have here is a global identifier, then again void, kernel, void. So this is global indicates that the function has to run, that particular function has to run on device, and that it gets called from the host code. So basically what NVCC does, that is the CUDA compiler does in this particular instance, it splits up your whole code into two parts. The host which runs on the CPU and the rest what runs on the GPU. NVIDIA's compiler will handle the kernel calls and the GPU required stuff, and the rest will be offloaded to the CPU based compiler. So that is generally GCC in case of Linux and Microsoft Visual C in case of Windows. That's how your code will look like if you are writing your code in CUDA. So I'm not telling that you should write your code in CUDA, but this is how it look like to give you an idea of how it works. So this is just a simple code. We are not going anywhere with compute or any copy operations. No complex code here. This is just a demo on that. Right. So this is called, this particular line highlighted here, that's kernel 1.1 call is called a kernel launch. So this is a very good example to tell you how this will translate in the backend into the hardware level. Right. So the kernel in this instance is a function which is called on the GPU. You have and this particular call will execute an array of threads in parallel. So one example is the kernel call which we saw earlier, which is kernel 1.1 call. So you basically you take the product of each of these arguments. So that's in this case 1 into 1. So that many threads will be running in parallel. So for the example of function call here, you will call 512 into 512 threads in parallel, right? So what these each thread does is each has its own ID. It has its own separate input and output data, as well as it follows its own state of control decisions. And this is just how it gets split up. Now, both you saw that there are two arguments and we took a product, right? So this is how that breaks down in the GPU. So these threads are grouped into blocks, and then the blocks are grouped into a grid. And then the kernel is executed as a grid of block of threads, right? So the first argument which we saw is the number of blocks, and the second argument relates to the number of threads per block. So I assume that is quite clear. So in our Hello World program, which we just saw, we have 1 into 1, that is one block with one thread inside, which will be run, right? Now, that is the case when you have to write a code in CUDA. So you can see that there is quite a learning curve here, right? But all the other SDKs which you generally work with or see, at least like CUDA and CUTensor, everything, generally almost always rely on the CUDA kernels which are running in background in the backend. So if you don't want to jump into CUDA, what are your other options, right? So that's where we come to the GPU computing platform for HPC. So I am talking about HPC here because all these libraries were initially started at the HPC level, made for HPC application. So these are the different ways to GPU computing. So generally, most of all of you would have been familiar with the GPU accelerated application. So if your application is already GPU accelerated, very well and good. Everybody is happy. They just have to install it in the system and you can just run it, right? If not, what if your application is not accelerated? Your next option is to see if any library fits your use case. And if so, if you can directly plug in your the libraries which are GPU accelerated, this the most easiest, it will give you the best performance, right? Now, if that is also not present, if your application doesn't even have the libraries which translate directly into your use case, if that's the case, what is the other only two options are compiler directives and programming language extensions. So the programming languages extensions is CUDA, which I just explained before, to give you an idea of how GPU works. So that will give you the most performance as well as, most flexibility for your program. Now, if you don't want to, but usually at the CUDA level, you will have to rewrite your entire application. You will have to check it for accuracy. You will have to run a bunch of tests to make sure that your code is working fine, right? Otherwise, you can go for compiler directives. This is a very good middle ground between the libraries and two programming languages, because it is quite easy to start. And generally, all the CPU, not generally, all the CPU-based compilers ignore these compiler directives because it's not associated with it, right? Hence, that makes it more portable as well. Your code, you can just pull it and put it in a non-GPU system and run, compile the code with your CPU compiler and expect it to still work. So that is where we come to the Open ACC, which is a compiler directive which do accelerate your code in GPU. There are a few domains where you do have, we already have applications accelerated across all these domains, like manufacturing, physics. So these are again in terms of HPC, and you have open GPU accelerated drop-in libraries like CUDA-X, TensorRT, DeepStream, and other domain-related stuff like signal processing, image, as well as parallel algorithms if your code demands. Right now, this concludes my introduction. Now we'll be jumping mainly to OpenACC and showing a simple program where you can just plug in the pragmas and make it much more performant. So what is OpenACC? It's a directive-based programming model, again, for parallel computing. And this is one example you can see in the middle where you just add some compiler directives. So hash will be our comments for the compiler and it will be ignored during compile time if it's not relevant to the compiler which is compiling it. And then it makes it more powerful and more portable. So if you are interested, if you have any application that requires you to jump into coding and accelerating at the very base level of your code, then the best place to start is NVIDIA HPC SDK, where you have it, all these tools which I've just mentioned, at least most of the tools for HPC development. You have your CUDA compiler, you have your OpenACC compiler, you have all your math libraries included, you have your profiler, and best of all, you have it available on NGC as a container. So you can always test your code, see if it works, and then you can add it to your AI deployment model as it fits. Let me jump on to my next presentation and I'll explain a bit more of OpenACC. Any questions till now? I can just maybe take one or two questions because we'll be jumping to OpenACC quite good. Okay, shall I move on to the next?
Sure.
Yeah, all right.
Without.
Was there a question?
Yeah, yes.
Please you ask.
Can we use OpenACC without the systems? Just with HPC?
Can you repeat the question? I think it was not clear.
Ma'am, there's some static on the call. So if you can type your question, we'll take that up.
Okay.
Hello.
Yeah.
I have a small question. If any student learns this CUDA integrated with C++, what are the opportunities? Are there any good opportunities in the industry for the student?
Okay, so it's from a learned perspective. If somebody already knows CUDA, right? So there are a lot.
If any student is interested in learning the CUDA, okay, with C++ integration, then what is their career? How their career will be?
Like I can't spend much time on this, but for a quick
just one word.
Yeah. So there are a lot of scientific applications currently in play, which are still not accelerated, which many industries still rely on, which need to be GPU accelerated. And most cases you do need CUDA for that. So.
So that means suppose because there are some research scholars, they are approaching us and they wanted to build their customized kernels. So they are very much interested in that. So in that case, can we suggest them to learn this CUDA with C or C++?
So what I will suggest more will be to learn OpenACC rather than CUDA, because CUDA basically requires you to have a deep understanding of the GPU architecture and the different things that bottleneck your system, right? Much more than any of the libraries, if you have used all the libraries, right? Now, OpenACC still allows you to work in the code level and exposes most of it via simple statements, which can help you still accelerate the code. And we do get very good performance comparison with CUDA and OpenACC.
Okay. Okay.
Right.
Thank
and
you.
CUDA basically can be used as a last measure, because when you talk about custom kernels, that is mostly there is because you don't have anything else to work in the code with, right? OpenACC solves most of that.
Okay.
Does that answer your question?
Yeah, thank you.
So, was there another question here?
I guess not, Isaac. So you can continue. I'm sorry.
I think Akshata.
Now am I audible? Yeah. Now am I audible?
Yeah.
Is OpenACC, can we use OpenACC without GPU, just with HPC clusters?
Yes, you can use the code. So OpenACC is Open Accelerate, stands for Open Acceleration, and it can even accelerate your the code on multi-core as well. But the best performance, again, if you have you type the code in that level, and if you want to move to a GPU, you can always port your code with minimal changes. That's the advantage of OpenACC.
Could we use some DL or ML applications in that?
That was not clear.
Could we use DL or ML applications on OpenACC?
So OpenACC will help you. So for example, if you do have a code or you have an application where you still don't have any wrappers, you don't have any libraries, anything to support what your flow demands, right?
Yeah.
Right. So some specific flow which the library is not optimized for. Now you know what the code should be doing. You know what it should actually do. You know that, okay, if I write the code myself, it will be much easier, right? So in your programming workflow, what you generally do is you just write your CPU level code, see if it works, right? So what I'm suggesting is at the next level, now if you want to accelerate that workflow, now you have, since you have the code ready, what do you do next, right? So you can either go with OpenACC or with CUDA. So at that point, you can introduce OpenACC, which will be much easier to plug in your code. That I'll be explaining in my slides now.
Yes, thanks.
Right. So let me share my next slides. Right. So these are the topics which we will be covering. So again, this is mainly covering OpenACC and why you should care. And I'll just show a program where you will accelerate using OpenACC. So again, this OpenACC, you can go to the website openacc.org and multiple websites of tutorials where you can cover most of the pragmas which I introduce here and much more on that. So OpenACC is a directive-based parallel programming model. It's a standard which is supported by OpenACC Foundation. So OpenACC is a standard, and NVIDIA does provide compilers which support the standard. Previously it was called PGI compiler suite. Now it is the HPC SDK, where you have your NV Fortran. You have extension to Fortran as well. You have NVC as well as NVC++, which are the other two compilers for C and C++ correspondingly, respectively, right? And this OpenACC is a compiler-based, directive-based programming methodology. And I'll just show a normal code which has OpenACC pragmas plug. So this is how you generally do OpenACC code So we'll be just covering the parallel portion here, which is the middle one, initiate parallel execution. The rest are a bit more advanced, but generally in a GPU based environment, you have other options to ignore the data movement as well. So the first one we won't be covering today, but the main thing here we'll be talking about is initiate parallel execution, that is hash pragma ACC parallel. What does that do? Right? So OpenACC directives are generally incremental. So you can plug in one pragma, see if it works, see if it is giving you right answer. Then you can add the next one for more optimization. And single source, meaning you don't have to keep multiple versions of it. It's essentially, since you're not changing your code, you're basically adding comments for the compiler. You don't have to keep on versioning your code. So that's another advantage of writing base CUDA. So when you write base CUDA, you might change some parameters. You might be moving something here and there. So that might cause some breakage of your code, and you still need to version it, right? So single source is what applies to OpenACC. And it's interoperable, performance is portable, and you can run this code, OpenACC compiled code on CPU, GPU, and multi-core, right? So that's what the strengths I was talking, incremental, single source, as well as low learning curve. So when you talk about incremental, so maintaining the existing sequential code, you add annotations to expose the parallelism. At the same time, you can verify the correctness and annotate more of your code as you go on, right? So you don't have to modify your CPU code, whatever code you have written for to run on CPU, you don't have to modify too much here. And another thing is single source, where it will work on all the different architectures, ARM-based, x86-based, NVIDIA GPUs, everything. Right, and the compiler can ignore your OpenACC additions if it doesn't support it. If the GPU is not available, it will just ignore that. That's all. Now, OpenACC programmability. So again, the pragmas tell where to run what kind of code, and that will be the compiler hint. In this case, hash pragma ACC kernels, and that will tell this code has to be run over the parallel hardware, whichever is available on the system. So here it's written kernels and parallel marker, which I told before. It's a bit different, but this is the example here. We'll discuss more on the parallel one actually. So OpenACC syntax, how does it look like, right? So you have OpenACC extension for C++, C, as well as Fortran. So in case of C++, you use hash pragma ACC, then some directive which does some particular thing, and the clauses which support your directive. And then in Fortran, you have something similar. You have exclamation dollar ACC, then directives and the clause. This will come above the code which you have to accelerate. Now in Fortran, as you know, it doesn't support braces or blocking. So you need to end each of your pragmas, each of your exclamation dollar ACC clauses when your code section ends, which you want to be parallel. So directives are commands for in OpenACC for altering your code, and clauses are specifiers or additions to the directives. Now let's jump directly into an example code where you can easily understand what I am talking about with all these directives and clauses. So one example, this is a HPC specific one. So I won't go too deep into it, but this is basically a Laplace heat transfer. So basically the code requires you to calculate the average of the 4 adjacent points, heat at the 4 adjacent points in the Cartesian system. Right, and this uses this Laplace heat transfer uses something called Jacobi iteration, which is quite parallel, which is very embarrassingly parallel. And if that's the case, so when I talk about parallel, that means each of your iterations is independent of each other in a loop. So how do I accelerate this? Using OpenACC. So this is how your code will look like. For example, so there is an outer while loop that is calculating the total error, and internally you have multiple for loops which are parallel, which are parallelizable, as well as each iteration is independent of each other, right? So just I'll just pause here a second if anybody wants to look through the code. So basically the first loop does calculate the average and does the maximum of error between all the newly computed and the previously computed values. And then later the next loop you just assign the newly calculated points to the old buffer, right? So you swap your input and output buffers. That's it. And the while loop continues until the error reaches a tolerance limit. You do have code constructs like this when you do machine learning algorithms or anything. You do have multiple parallelizable loops, which might not be available in the libraries, and you still have to accelerate it. So that is where OpenACC parallel loop directive comes in. So if you think about this particular slide here, from a CUDA perspective, you need to do much more than just parallelize this. You need to rewrite this entire code, right? Which will make it more efficient. But what OpenACC helps you do is do the computation. At the same time, the compiler will take a bit more, do some extra steps to optimize your code as it goes on. So let me show you what I mean by that in the parallel loop directive here. So there is as I explained before, you do have blocks, and in blocks you have threads, right? That is how GPU executes the code. So when you tell parallel, it basically tells that this particular loop has to be different blocks. So in OpenACC, it's called gangs, right? Each gang is a block. And so, for example, in this particular case, you have a loop starting from I equal to 0 to I equal to n minus 1, right? So you will have n blocks running in parallel. So now I just mentioned these will be n blocks, right? That means that you will have multiple threads running concurrently per block doing the same exact thing. So each iteration of this particular loop here, that is starting from 0 to n minus 1 will be each iteration. So for the first block, you will have 0th iteration in multiple threads running at the same time, right? So that is just the nature of how it works, and let's see how you will apply that. So when you put Pragma ACC parallel loop here and do an assignment, the compiler will take care that, okay, there is only one loop which is available to me, right? I cannot do it. I can do it on the GPU, but at the same time, I'll be doing it on per thread, right? So the compiler will optimize it in such a way that you still get the same performance if it was just running threads individually. So to parallelize multiple loops, each should be accommodated with the parallel directives. Each parallel loop nest can have different loop boundaries and loop optimization, right? So, and each of this nests should be parallelized in a different way. Now let's come to this example where we just left off. Now you add the Pragma ACC parallel loop. Let's just ignore the reduction clause for now. But what it does is it notices that, okay, I have a first loop here, the first J loop, which can be done in per block, right? Now you sees the second loop as well, and it sees that, okay, each iteration of the I loop is also independent of the J loop, right? So what it does is the J loop will be handled at block level, your I loop will be handled at thread level. So essentially what you're still doing is what is handled in CUDA, right? This is again a kernel launch, what we discussed quite previously, where you have so in that case, you will have J blocks and you will have I threads per J block, right? Per J block. And that's how you run in OpenACC. And similarly, for the below one, you do have again two loops. So that will again accelerate it, similar to what I told. Now, what is this reduction doing? So this reduction is something which is quite a bit dependent on per iteration, but at the same time, reductions operations are also inherently parallel, not in the same way as this loop here. So the reduction clause takes many values and reduces them into a single value. So at that, in this particular scenario, you can mention it to the OpenACC. Tell them, okay, this particular value will be generated in all my iterations. Now, at the end of my block, please do convert them into a single value, and you just provide the compiler with what kind of operations should be used to reduce it to a single value, right? And this will also be handled in parallel inside the GPU. So if you are going to write that in CUDA, that will take you much more of a time, right? At the same time, you can just use the reduction operators, or in this particular case, you have max of error. So you are actually calculating the max of error, and you can see that, okay, the code is here. I need to calculate the max of the error values generated for all of these. It will do that. Now, how do you build the code? I will move a bit fast on this because we'll just focus on, let's say, this current code. So to compile this was when we were using PGA compiler. This is PGC++ or PGC, whether it's a C++ or C code. And -fast tells that do optimize the code to compiler's best of abilities. And then this is for logging, giving you some information about how the optimizations have been done. So just minfo Axel will give the accelerated code optimizations which has been done, and opt will give the other code optimization. All will give you all the code optimization, whether positive or negative. So generally, when you're coding, it's advisable to give minfo equal to all. And this is where you avoid the problem of CPU to GPU transfers. So in the latest versions of CUDA, we have introduced something called managed memory, where the compiler, if intelligent enough, can handle all the memory transfers. So this has grown to the point where you do get similar performance when you use managed memory versus manually moved data movement, right? So here in this case, we are this TA equal to Tesla means that it's accelerated code for NVIDIA GPU, that is the Tesla brand. And then manage stands for managed memory. So data movement should be automatic. I don't want to worry about the data movement, so please handle it for me, right? And mCUDA this is for some timing things. Let's just keep this. Now, this is what will your code look like when you finally compile it, right? So here we have given minfo equal to acceleration. So it will give all your information about how the code is accelerated. It will tell that, okay, so if we come back actually to the lines of code, we'll see that we had two separate loops, right? Two separate double loops which we accelerated. So accelerated kernel region generated. So the 64th line, you have a loop gang. So that will be the block IDX. If people are familiar with CUDA, that is the blocks. And then the 66th line will be the threads. Similarly, for the next loop, you again have something like that. Okay. And here, if you see vector of 128, meaning you have 128 threads per block. And how does the acceleration look like? This is how. So if you in OpenACC, you do have, I mentioned, there is an option for multi-core acceleration that you can enable if required, but that is not entirely necessary if you are directly jumping to GPU code. So that will be just controlled by your -TA equal to multi-core or -TA equal to Tesla managed. And if you are doing -TA equal to Tesla managed on a NVIDIA V100 on that code, which we just saw now, you get a 34 times performance improvement directly. All right. So this is generally how you do in OpenACC. And I just told you a compare and contrast between how you would face issues in CUDA if you are thinking of doing it in CUDA. Right? And so what are the key modules we just covered? It's what is OpenACC, how to parallelize the loops using OpenACC's parallel loops. So this is just an intro of how you start using OpenACC, and you just generally just need the parallel loop for the very trivial of cases. And you have other OpenACC resources. We'll be sharing the slides, so you can go through that also if required. So any questions?
Am I audible?
Yeah, you're audible. Please go ahead.
So do we have any extension or any support for Python related scripting languages or any other scripting languages apart from C, C++ or Fortran?
Okay, so that is a very good question. So you do have it's not a do have. So the general case in Python is it's an interpreter scripting language, right? So all your code generally what happens is it is not optimized for performance, right? But so if you think about it, if you were actually typing all the code, you are actually typing all the loops, how it should interact, how the data should be handled. In Python, it will be much slower than a C, C++ code, right? You could think about it like that. If you're actually doing all the loops and stuff. Now, that is why it is done in C, C++ or Fortran, because those are compiler based languages. So if you think about it, if you try adding pragmas, the C or the compiler doesn't know, there is no compiler here, right? So it doesn't know ahead of time where to start, where to stop, how to parallelize it. So all these details won't be there. So this has all the code has to be run through at least once to know which all places can be optimized where you can get the best performance, because this is the basic building block of your entire application. So if this is not optimized, your entire application will suffer, right? That's why we go with C++ Fortran because they are
maybe more compiler oriented programming languages rather than scripting languages.
Yes, exactly. Because we need the performance at this level. If we lose, again, this comes back to the full stack development. So if we lose the performance here, that will affect your application in a big way.
Yeah. But when we speak about the containers, what they mentioned in last session, all those DL or ML applications, basically those frameworks will be written either in TensorFlow or Python related platforms or notebooks. So in that case, how do we use OpenACC to accelerate the training or compute expensive parts in them?
You are thinking about how do you go about doing this, right? So really what you have is, so if in your AI or ML or DL application, you have some place where you are facing this particular bottleneck, right? So you do prototype in Python, right? Generally.
Yeah.
Then you write, let's assume that, like there are, excuse me, there are libraries like CUDA-X. If you are proficient in that, you would know that these libraries do call Python wrappers for your C, C++ backend code.
Yes.
So in for that cases, you need to write some wrapper like this, which will call the C, C++ code and define it to call that particular module and execute that in C, C++. And then
kind of wrappers can be used.
Exactly. So you do prototype with Python. You write your hello. My voice is not audible.
Yes, sir. Yeah, it's audible, sir.
So you prototype in Python. You write your C code, which is a bit more optimized. Then you go about adding your what do you say, OpenACC pragmas. Make sure the results you give are correct. You are getting are correct. Then you write findings.
One more query, sir. This was of great help. One more query I had. So, do we have any kind of difference or similarities between MPIs and OpenACCs in parallelizing?
Okay, MPI, right? So, you're talking about MPI call, right?
Yeah, MPI. Basically, Open MPIs or Intel MPIs.
Yeah. Okay. So MPI is actually a different architecture and programming model in it. So when you talk about MPI, it is process communication when you are spawning multiple. Here always we are talking about a single application working on a single GPU, if you think about it. Right. So when you have to work, hello, am I audible?
Yes, you are.
Yes, sir.
Okay. So when you are working with environment where you have multiple GPUs, you still need tools like MPI to spawn multiple processes which will do the data decomposition first, and then offload each process data to the available GPU.
Okay. Here we use for accelerating the computation. Hello?
Yeah.
If I'm understanding correctly, we are using this for accelerating the computational expensive parts of a code in a single GPU or a CPU. Am I right, sir? I mean, if I'm understanding correctly. Hello?
Hello, am I audible? Sorry, I just lost my internet connection. Can you just repeat?
Yeah, I just wanted a confirmation that if I'm understanding it correctly, we are using this Open ACC platform for accelerating the compute expensive parts of a code in a single GPU or a CPU in an HPC. Am I understanding it correctly, if I'm not mistaken?
Yes. What I explained is for a single GPU, but you do have extensions in the OpenACC itself if you are on a multi-GPU platform. That can extend to it. At the same time, these extensions should work together with MPI. MPI should be running beforehand to know that, okay, you have split the data, and then the OpenACC can tell that there is mechanisms in OpenACC to identify which GPU it should run on. Make sense?
Yes, sir. A lot. Thank you.
Yeah. Any more questions?
Isaac, we have a question, which is, what are the compilers available for Open ACC compilation?
Right. Okay. So, sorry, I didn't see the chat. So basically for OpenACC compilation, the best method right now is you download the NVIDIA HPC SDK or download the container of HPC SDK if you have more hands-on with the containers. You do you have all the required compilers there. So the specific ones here are NV Fortran for Fortran based OpenACC code. You have NVC for C based code, and you have NVC++ for C++ based inside NVIDIA HPC SDK. And another thing here is generally in HPC SDK we package multiple versions of CUDA. So there is an option to choose which version of CUDA is compatible according to the requirements. That's an entirely different topic, but yeah, there is a lot more to explain there. But to answer your question, you have all the compilers required inside HPC SDK. Specific ones are NV Fortran, NVC, and NVC++.
Thank you for that, Isaac. We have other questions, but we'll take it at the end of the session. So
sure. Yeah, the session is done. Like I have completed. Yeah, NV HPC SDK is freely available. Yes, you can download it on the website. I'll just post that link on the chat.
Okay. So are we open for more questions, Isaac?
Yes, we are open for more questions.
Okay. So you can please ask any question if you have. You can unmute yourself and you can ask the questions. And in the meanwhile, I would also like to inform you that you will receive a survey on the presentation, and we would really appreciate if you would provide your valuable feedback. And we have a lucky draw wherein we'll decide on winners based on the survey forms. So do take some time to fill the survey form for us.
Okay, is that end of the session?
Sir, if there are questions, we'll definitely take the questions. Or, if we are done, then, in that case, Isaac, is there anything else you wanted to cover before a wrap up?
Yeah, so the topics I discussed, including CUDA, OpenACC, NVIDIA HPC SDK, they are just very, very base level. So this was just to give an overview of the options available to accelerate your application. And in case you want to actually get on with doing it, I suggest you thoroughly research a bit. So in terms of ease of use, you will have OpenACC in the top and CUDA below that. But in terms of flexibility and maximum performance, you always have the best performance in CUDA. But again, I would suggest do start with OpenACC because for most of the cases, you get similar performance in OpenACC as well. That's all. That's where I'll try to stop.
Okay. Thank you so much for that, Isaac, and thank you everyone. With this, we come to the end of the webinar. It was a pleasure being with you today. If you have any questions, please reach out to us. I will put my email ID in the chat box. And thank you everyone. We really appreciate you being here. Thanks again for joining us today, and we will see you next time. And do make sure that you fill the survey form, and we'll get back to you with the announcement about the winner.
Please send all the slides also.
Yes, sir. We will definitely share it along with the slides that we have presented today.
Sure. Thank you all.
Thank you all for your time. We really appreciate you being here.
Yeah. Yeah. Thanks a lot. This was very informative. Yeah,
thank you, ma'am. We really appreciate it. Ma'am, do fill the survey form. We would really appreciate that.
Sure, ma'am. Thank you.
Thank you.
Thank you.
Stay safe. Take care. Thank you.